In this session, we look at section 14.2, dealing with the k-means cluster analysis approach. And so in this approach, basically, we have to specify in advance the number of clusters that we want to develop. And there is an iterative process then that is executed to find the best clusters, the tightest fitting clusters, as we might say. So the procedure is kind of delineated down here in our inset box. It says the k-means clustering method assigns each observation to a cluster, and such that the observations assigned to the same cluster are as similar as possible. Now, the number of clusters, k, is determined prior to estimation, so that means that you need to typically have some knowledge of your data set and how it's likely to cluster. We saw an example in a previous section where we were dealing with income levels, poverty levels, crime rates, and so forth. And there was, you might say, some intuition that could be applied to that data set to discern how it's likely to cluster. And so, again, it's that sort of knowledge that you would kind of bring to the table to implement k-means clustering. And of course, you can do multiple runs with k set at different levels and see what the results happen to be, and choose from the best set of results. So that is one approach. But again, the number of clusters, at least for a given run, is determined prior to estimation. The k-means clustering method can only be applied to data with numerical variables. So if we've got mixed data, then we have to revert to the methodology of the previous section. Okay, so the general process of the k-means clustering algorithm can be summarized as follows. So we just specify again in advance how many clusters we're looking to form. So that's the k value. We randomly assign k observations as cluster centers. Okay, so we have a set of 200 observations, and k is 5. We randomly choose 5 of our observations and designate those observations as cluster centers. We assign each observation to its nearest cluster center. Okay, so we begin working with those as the defined centers. Assign each observation to its nearest cluster center. So that means you got to calculate distances between all of our observations and those points that we've identified as the initial cluster centers. And so once we've made those assignments to the k clusters, we then calculate the cluster centroid. So again, basically you're doing an averaging of the values there that based on the metrics that are used to define the clusters to calculate the centroids. Reassign each observation to a cluster with the nearest centroid. Okay. And then recalculate the cluster centroids and repeat step 5. So you get these iterations going where you're reassigning to a cluster and then recalculating the cluster centroids and back and forth. So eventually you converge to a result where you can no longer improve, as we noted here in item 7, the within cluster dispersion. So you've arrived at the clusters that are as tight as possible, the k clusters that are as tight as possible in terms of the distances within the clusters. So the distances from the calculated centroids. And so again, you might say, well, it may depend on the k observations you start with, but the idea is that it will gravitate to or converge to the same result, depending upon whichever k observations you select, and that will generally be the case. Okay, so they do note here, compared to the hierarchical clustering methods that we talked about in our previous section, the k-means clustering method is more computationally efficient, especially when dealing with large data sets. That's because hierarchical clustering requires computation of distances between each pair of possible observations, while k-means clustering only requires computation of distances between each observation and the cluster centroids during each iteration. So again, it becomes more efficient in terms of calculation, processing time, that sort of thing. So let's go ahead and look at our example for this section. It's example 14.3. And says, recall that the objective outlined in the introductory case is to help Williams group candy bars into meaningful clusters and improve product selection and display for vending machines. Perform k-means clustering analysis or clustering on the data to create 4 clusters and interpret the results. And again, I think in terms of just defining, say, the number of clusters you want to, or identifying the number of clusters, you want to think in terms of your ability to describe those clusters. We'll look at the R approach here. There's the analytics solver that you can go through if you would like to, but again, I think you'll find R the most useful to you on down the road, and that's why I kind of have emphasized it in the examples, the lectures that I've presented throughout this term. So we'll import the candy bars data into the data frame and label it my data as we've done before. We need to load the cluster package, and so if you have an installed cluster, you need to do that. Okay, so you can just execute that in the bottom window down here if you want to. And if it hasn't been installed, you can tell quickly if it's been installed by just going to packages over here, going down the list here, and seeing if you find cluster in the list. If you don't find cluster in the list, it means it hasn't been installed, so you need to do that. Install packages and then cluster in double quotes surrounded by parentheses, and that'll take care of that. So then after that, get back to the right spot in my notebook here. Okay, you'll do the library cluster to basically load the package. The alternative is just to check mark it over here. It will execute that. So either click here or just simply do the check mark there, and you've got it now available to use. And so we've talked about many times how to bring data into R. And so again, you can use the import dataset tool here. I'm going to clear this out. I think it's always a good idea before you really start doing analysis, go ahead and clear out anything you've got here so it doesn't create confusion, or you don't wind up processing data into your analysis that's not intended. So kind of sweep the environment clean. You can even sweep this area clean if you want to. And we'll read the data in. So again, it's the candy bars worksheet within the Chapter 14 workbook. And we'll execute that, take a look at our data. So we've got the various brand names here. Most of those probably recognizable, I'd say. Some of those I haven't heard of. I'm not sure what Chunky is, and a few others, but you perhaps have heard of those. Some of these go way back, way back. So anyway, we've got the data, and we've got the items or the features, attributes of interest, calories, the fat content, protein, and carbohydrates. And we'll run the k-means cluster analysis. We want 4 clusters, so k equal to 4. So we do have the data in, and kind of get back again to my, that's not the right notebook there. We'll get back to the correct notebook here. And we will be making use of the random number generator. So that we get the same results that are obtained in our textbook, we want to use the same version of the random number generator. And of course, then that being an older version, it will create some warnings along the way, so we'll suppress those warnings. All right, so that just sets that as our random number generator. And then, as noted here, we exclude the brand variable from the analysis. Okay, keep in mind we can only work with numerical data here in the k-means cluster analysis approach. And so even so, we would leave the brand variable out and standardize the other variables using the scale function. The new data frame we'll just call my data std underscore std. And so we use the scale function there on my data operating on columns 2 through 5 of our data. So columns 2 through 2, 3, 4, 5. So 4 columns of data. And when we do that, we'll see a new data set appear over here. We could look at it. We could do a view my std, and so view my data std. So I re-execute there. And just take a look. This is what your data will look like, standardized. So again, everything's a z-score. So the number of standard deviations from the mean that each observation is for that particular attribute. Then we're ready to move along. Use the set seed function to set the random seed and the PAM function, is what it should be here, PAM, to perform the k-means clustering. The acronym PAM stands for partitioning around medoids. Okay, so should be around medoids. Okay, so just another way of saying or describing the k-means clustering approach. So within the PAM function, we set the option k to 4 because we have selected 4 clusters. We store the cluster results in a variable called k-result, and as noted here, a medoid is the observation that is closest to the center of the cluster. Okay, the observation that is the center, to be contrasted with a centroid, which may not actually coincide with an actual observation. Okay, the medoid is the observation that's closest to the center of the cluster. So we set random number seed to 1, so that we'll basically obtain the same result as obtained in our textbook. So again, we're working on the standardized data, and we're setting k equal to 4, so specifying that we're going to have 4 clusters, and PAM is the function, and we'll get a summary of our results. So let's go ahead and execute there. Okay, and so you'll see the identified medoids here, what the observation number is. 9 is the medoid. Observation 9 is the medoid for the first cluster. If we were to go back and look at number 9 here, you'll see 0.808, 0.599, and so forth. So that does correspond with the values you see here. Okay, so observation 9 is identified as the medoid there of cluster 1. Cluster 2, it's observation 18. Cluster 3, observation 24. And then for cluster 4, it's observation 35. Okay. So then we have our clustering vector, which just basically shows if you were to go through the observations and assign the cluster numbers to those observations, this is the pattern that would result. So it gives us the first several of these. Okay. Keep in mind back here in our data, we just had 37 observations of 5 variables. So you might be seeing all 37. You could count them there, but anyway, we'll move along here and then look at the plot, I think, at this point. Okay, so the next thing we'll want to do is plot the result. So let's go plot k-result. So the first thing we'll see here is a graph that looks somewhat like what is in our textbook. If we go down here, you'll see that it's kind of in a way, the mirror image of what appears in our textbook. You've got the long elliptical shape cluster showing up on the lower left hand side here, whereas it shows up on the lower right hand side in the textbook, and so forth. But if again you just kind of examine the two, you'll see that it's basically the same graph. It's just one's kind of the mirror of the other. What it really does is it uses principal component analysis. Recall we discussed principal component analysis a couple of chapters ago, and we were looking at it was a method of data reduction, if you recall that, where we might have several correlated variables, predictor variables in an analysis, and we can reduce those to a set of uncorrelated principal components, which are kind of a weighted sets of the original attributes or features that we were looking at in the data. And so since we're dealing with 4 features or 4 attributes in this analysis, you obviously can't plot groups based on 4 dimensions. Okay, 3 dimensions is difficult enough, but you can kind of do a diagram that might show that. But when you go to 4 dimensions, obviously you can't do that. And so the solution here is to reduce the 4 attributes for graphical purposes, to 2 principal components. So you're in 2-dimensional space now, and then you can see how the observations cluster relative to those principal components. Okay, and we could perhaps change signs on the principal components as calculated, and flip our graph so that it looks exactly what's like in the textbook. But the idea is you're just kind of getting a sense of the reasonableness of the clustering, and see to what extent the clusters kind of stand out from one another. There's a little bit of overlap here. You got a little overlap here, a little here, but overall it appears that we have pretty good clustering going on there. There's another graph that's presented. It's the silhouette plot. There was some data presented up here, the silhouette plot information, identifying the various observations that appear in each cluster, and then this silhouette width. If we kind of examine the plot of that, then based on the silhouette width here, we'll see that we have our observations for cluster 1 showing up here. Then you've got cluster 2, and then cluster 3, and cluster 4 down here. And just kind of noting here in terms of the description that provided for us by our authors, it says the silhouette plot shows how close each observation in one cluster is to observations in the other cluster. It allows us to visually determine the appropriate number of clusters. So the silhouette width for each observation ranges from a -1 to a +1, where a value closer to +1 indicates that the observation is well matched to its own cluster and poorly matched to neighboring clusters. Okay, so if most observations have values close to +1, the clustering configuration is appropriate. And that's kind of what we're seeing in general for cluster 1. Most of the observations are indeed in the positive territory. Okay, keep in mind the widths can go from -1 to +1, but they've got a rank ordered here, decreasing order of silhouette width. Okay, so and then you'll see a break here in between silhouette 2 and silhouette 3 here. Okay, or between cluster 2 and cluster 3. And so you see the natural breaks that seem to occur in here, and indicates that we've, again, I think, done a reasonable job in terms of identifying the appropriate number of clusters. Okay, so once you have the clusters identified, we've got the cluster numbers here, the observations and so forth. It might be nice to go back and append those cluster assignments to the original data. And to do that, we'll use the data frame function. We'll combine my data with the um, K results clustering. Okay, so if we go up here, get K results, and then there's clustering as one of the fields here. This is where the assignments of the clusters are. So within the K result data field, we've got the clustering field. The K result data frame, we've got the clustering field, and these are the cluster numbers. Okay, and we just want to combine that with the original data, and we output the result back over my data, and then as noted here, we can then change the name of the column that shows up there as K result clustering. If you just stop at that, you'll have a column that's labeled K result clustering, and if, just for maybe workability on down the way, if we just want to relabel that as clusters, then this is the command that will effectively do that, and then we can view our data. Okay, so there we have it. Okay, so the original data and then the cluster assignment there. Now it's perhaps interesting if we do some run some stats on those clusters just to see if there are things that stand out. If we were to provide, say, a label to the clusters to describe the membership of the clusters in general, what would that be? So we can do the summary function, apply the summary function to a subset of my data, where basically we're looking at those observations where clusters is equal to 1, and then where clusters is equal to 2, then clusters equal to 3, clusters equal to 4. And so we can execute that. And then basically it's a matter of just kind of perusing the data. This is cluster 1. Okay, you can see what the mean is for calories and fat and protein, carbohydrates. And then cluster 2, you can see what the mean is for those, and kind of compare those across. You'll have some of the candy bars higher fat and so forth content. You might distinguish them on that basis. Certainly, I think the protein feature here is one. You've got on protein here, cluster 1, high protein, I'd say, relative to the others. Cluster 2 is pretty low, and so forth. So again, this kind of allows you to describe, based on these 4 attributes, the membership of the clusters. And so let's see if there's anything else there that they actually kind of stop the analysis there. I thought it's good to go ahead and reattach, you might say, or align the cluster assignments with the original data, and then, like I say, get those stats so that you kind of see from a practical standpoint what you really do with this analysis and its accompanying results.